So we're going to go over again the construction of a quotient group and show how these are related to group homomorphisms. So the idea to have in mind is congruence classes. So we let Z be the additive group of integers. Every subgroup is of the form m times z for some positive integer m, and the left cosets of mz, which are the same as the congruence classes, mod m, these are sets of the form x plus mz. So this is everything of the form x plus mk, where k is an integer. And there is a well-defined addition operation of congruence classes. So what that means is that if you take the congruence class x plus mz and the congruence class y plus mz, you can add them by defining the sum to be the congruence class of the integer x plus y plus mz. And what this means to be well defined is the following. So this is well defined, or this works, because if x1 plus mz equals x2 plus mz, so we have one congruence class, but maybe two different representatives in how we write it down, and y1 plus mz equals y2 plus mz, then when we add x1 plus y1 plus mz is the same as x2 plus y2 plus mz. Let me just write down an example to show what I mean. Suppose we take the modulus m to be equal to 9. So we have, for example, that 5 is congruent to 50 mod 9. So the congruence class of 5 is the same as the congruence class of 50. And we have also 22 is congruent to minus 7 mod 9. So the congruence class of 22 is the same as the congruence class of minus 7. So we have different ways to write the same congruence class. If we take 5 plus 9z and add it to 50 plus 9z, we get 55 plus 9z by our addition rule. If we add 22 plus 9z to minus 7 plus 9z, we get 15. Plus 9z. But these have to be the same because these two congruence classes are equal and these two congruence classes are equal. But what about these? Let me make sure I did my arithmetic right. 50 minus 5 is 45 is divisible by 9. 22 plus 7, oops, I'm sorry, this should have been a 5. 22 is not congruent to minus 7. 22 is congruent to minus 5. So this is minus 5, and this is 17. Ah, now this should be better. These are equal because 55 is in fact congruent to 17 mod 9. Because this difference, 55 minus 17, is 30, oops, it's 38. 55, 5 take away 7 is 8, 38. So why is my arithmetic wrong? So 5 is congruent to 50. And 22 is congruent to minus 5. And 5, oops, I made this, I did this all wrong. Now, but I'll make it correct. So when I add 5 plus 9, 7, plus 9, 7, the congruence class of 5, and the congruence class of 22. That's the congruence class of 29. Mod 9. And if I take the congruence class of 50, and I add it to the congruence class of minus 5, I get the congruence class of 50. 5 is 50. So 5 plus 22, my arithmetic is terrible today. 5 plus 22 is 27. Oh, that's good. And 50 minus 5 is 45. And in fact, these are the same congruence class because 27 is congruent to 45 mod 9. So here I take one congruence class. I could represent it with a 5 or with a 50. Here's a second congruence class. I could represent it with a 22 or a minus 5. When I add, here I get 27, here I get 45. The different representatives, different elements in the congruence class that I'm choosing to represent the congruence class. But it's the same congruence class. So this addition is well defined. Okay, that was hard. So we want to generalize this construction. So if we're given a group G, like the integers, and a subgroup H, like the multiples of 9, would like to construct a binary operation, a multiplication, on the left cosets So this is the set of left cosets of H that makes the set of left cosets a group. And the problem is you can't always do this. Oh, and we like a binary operator makes it a group, and we want to define the multiplication of two cosets as follows. If you have the coset XH and the coset YH, we want the product to be equal to XY times H. That's the multiplication we would like to define on the left cosets, because that's a nice generalization of congruence classes. And unfortunately, You can always try to define it like this, but the problem is this is not necessarily well defined. Sometimes it doesn't work. So let me construct an example where it fails. Let's take S3, the symmetric group on three numbers, 1, 2, 3, the permutations of 1, 2, 3. And we know this group has 6 elements. There's 6 ways to permute 1, 2, and 3. There's the 3 cycle 1, 2, 3, the 3 cycle 1, 3, 2, and the transpositions 1, 2, 1, 3, and 2, 3. So these two elements of order 3, a transposition is order 2. Consider the subgroup H consisting of the identity and the transposition 1, 2. So let's compute, let's look at some left cosets. We have the left coset 1, 3 times H. So that consists of the elements, we multiply everything in H on the left by 1, 3. 1, 3, and 1, 3 times 1, 2, which is equal to 1, 3. And when you multiply 1, 3 by 1, 2, 1 goes to 2, 2 goes to 3, and 3 goes back to 1. So this left coset consists of the transposition 1, 3 and the 3 cycle 1, 2, 3. Suppose I take 1, 2, 3 times H. So this consists of 1, 2, 3 and 1, 2, 3 times 1, 2. So that's 1, 2, 3. And if you do multiply 1, 2, 3 and 1, 2, this is 1 goes to 2 goes to 3, 3 goes to 1, and 2 goes to 1 goes to 2. So these are equal. So in the symmetric group S3, the coset 1, 3 H is equal to the coset 1, 2, 3 times H. And, and we also have, if you take the coset, for example, 2, 3 times H, that's certainly equal to itself. Let's just make it easy. So suppose we multiply. If we multiply this and this, that's 1, 3 H times 2, 3 H. So if our multiplication rule works, this would have to be 1, 3 times 2, 3 H. See, what is 1, 3 times 2, 3? This sends 1 to 3, 3 to 2, 2 to 1. 1 goes to 3, 3 goes to 2, 2 goes to 3 goes to back to 1, and 3, let's see, 1 goes to 3. Let's do it correctly. Let's do it really correctly. So 1 goes to 1 goes to 3. 3 goes to 2 goes to 2. 2 goes to 3 goes back to 1. So this is the coset 1, 3, 2. And if I take this times this, 1, 2, 3 H times 2, 3 H, that would be the coset 1, 2, 3, 2, 3 H. What is 1, 2, 3 times 2, 3? 1 goes to 2, 2 goes to 3, goes back to 1, and 3 goes to 3. H. So this is 1, 3, 2, 1, 3, 2, 1, 2. And this is 1, 2, 1, 2 times 1, 2, which is the identity. So these are different. Let's see, what is 1, 3, 2, 1, 2? 1 goes to 2, goes back to 1. 2 goes to 3. This is just 3, 2. So when I multiply this, I get the set of permutations one, 3, 2, and 2, 3. And when I multiply this, I get E and 1, 2. And these are different. So the whole point of this calculation is, in this example, for the symmetric group S3 and the subgroup H, my attempted multiplication of cosets doesn't work. It's not well defined. And let me make an observation about this subgroup to indicate perhaps not necessarily why it's not well defined, but just something about the subgroup H. Suppose I take, for example, the left coset 1, 3 times H. So that consists of 1, 3 and 1, 3, 1, 2, which is 1, 3, and this is 1 goes to 2, 2 goes, and the cycle 1, 2, 3. Let me look at the right coset, H1, 3. So that consists of 1, 3 and 1, 2, 1, 3. So that is 1, 3, and this is 1 goes to 3, 3 goes to 2, 2 goes back to 1. These are different. This and this, these are different permutations. So the left coset 1, 3, H is not the same as the right coset H1, 3. And it turns out that that's the problem. So if for a given subgroup, every left coset equaled the corresponding right coset, then we would be able to define multiplication of cosets in a consistent way. So the name we give to a subgroup whose left and right cosets are equal is normal. So a subgroup H of G is normal if XH equals HX for all X in the group. So if you have a subgroup H with the property that you take the left coset XH and you take the right coset HX, they're always the same sets. And there's a theorem that says if H is a normal subgroup of G, then coset multiplication is defining XH times YH to be XYH is well defined. It's a well-defined binary operation. So it's a well-defined operation on the set of left cosets, and G mod H is a group with this multiplication, which is called the quotient group. So let's prove that this multiplication is well defined. Proof. So suppose we take XH, a coset, and YH. So this is a product of two sets. And so let me just maybe do this in a slightly different way. So XH is everything of the form XH1, where H1 is in the subgroup. YH is everything of the form YH2, where H2 is in the subgroup. And when I multiply these two sets, I get everything that you can write as XH1, YH2 for all elements H1, H2 in the subgroup. But H is normal, which means YH equals HY, which means for every H2 in H, there is an H3 in H, such that YH2 equals H3Y. Any element which is Y times something in H can be written as something else in H times Y. So I should write this. Any H1 in H, there's an H3, says YH1. I'm still going to get this right. So I have H1Y. For every one H1 in H, there is an H3 in H, such that H1Y equals YH3. So this element can be actually written as XY H3H2. And this is an element of H. This is in the coset XYH. And if you take anything in XYH, you can write it as XHYH. So that's a good proof, but let me do it again in a slightly different way. So H normal implies that HY equals YH for all Y in the group. So if I look at the product set XH times YH, that's the product of X times H times Y times H. But H times Y is Y times H. And H times H is H, because H is a subgroup. So the product of these two sets, whatever is in them, is this. So therefore, we can multiply left cosets. And now all the properties of the group are easy to check. Associativity. If you take the coset XH and you multiply it by YH, and you multiply that by ZH, this is XYH times ZH. this is xy times z times h. But because G is a group, multiplication and G is associative, this is x times yz times h, which is xh times yzh, which is xh times yh zh. So that's associativity. What's the identity coset? Well, the left coset EH, which is the same as H, because if you take XH times EH, you get XEH, which is XH. And EH times XH is EX times H, which is X times H. So that's the identity element. And for an inverse, if you take the coset XH times the coset X inverse H, you get the coset XX inverse H, which is EH or H. And if you multiply in the opposite order, you get X inverse XH, which is EH, which is H. So the inverse of the coset XH is the coset of X inverse H. So we have just proved that if you have a normal subgroup, there's a natural multiplication on the left cosets. Let's define a homomorphism of groups. A function f from a group G to a group G prime is a group homomorphism, or just a homomorphism for short, if the following is true: f of x times y is f of x times f of y for all x and y in the group. Again, here I'm writing both groups multiplicatively, and I've already written down what this equation would look like if G or G prime or both were additive. What are some nice properties of a homomorphism? So let me just collect them in sort of a lemma. So if you apply f to the identity in G, you get the identity in G prime. If you take f of x, x is in G, so f of x is in G prime, the inverse of f of x is the image of f of x inverse. How do we prove these? Well, we know that E is E times the identity. So f of E, that's f of E times E, that's equal to f of E times f of E. So multiply by whatever f of E's inverse is. You get f of E inverse times f of E is f of E inverse times f of E times f of E. F of E inverse times f of E is E. And these cancel, and this is f of E. So this proves one. What about two? Well, E is equal to XX inverse. So f of E, which we know is the identity, is f of x times x inverse. Which is f of x times f of x inverse. So if you multiply by f of x inverse, you get f of x inverse is equal to f of x inverse times f of x times f of the element x inverse. This is the identity, so it cancels. This is f of x inverse. So that's the proof of this little lemma. What's more important is the following. So we have this f from g to g prime, a homomorphism. I'll just state this as another lemma. So what is called the kernel of f, it's all elements x and g such that f of x is equal to the identity. And the image of f, which we sometimes write of f of g, is everything of the form f of x for x and g. So this is a subset of g, but this is a subset of g prime, because you take an x, here's f of x over in g and g prime. So everything over here, which comes from something in g, this is f of g. If this is the identity and this is the identity, this goes to that. Now sitting over here, you have some elements that all map to the identity. This is the kernel. So how do we prove this? So to show that, let me just write down what I said. Kernel of f is a subgroup of g. The image of f is a subgroup of g prime. So to prove something is a kernel is a subgroup, you have to show it's closed under multiplication. So let x and x prime be in the kernel of f, which I'll just call k. That means that f of x and f of x prime both get mapped to the identity. So f of x times x prime is f of x times f of x prime. That's the identity times identity. That's the identity. So x times x prime are in the kernel. So the kernel is closed under multiplication. We know by what we just proved that f of e equals e. So the identity is in the kernel. And if x is in the kernel, implies f of x equals e, implies the inverse of f of x is the inverse of e, which is e, but the inverse of f of x is f of x inverse. So x inverse is in the kernel. So you put these three properties together, the kernel is closed under multiplication, contains the identity, contains the inverse of each of its elements, therefore the kernel is a subgroup. What about the image? So we know that f of e, if e is the identity in g, f of e is the identity in g prime, so that is in the image of f. Now let me show that the image of f is closed under multiplication. If y and y prime are in the image of f, then there exists x and x prime in g, with f of x equals y and f of x equals y prime, f of x prime equals y prime, which means y prime is f of x times f of x prime, but because f's a homomorphism, this is f of x prime. So the image of x prime is y prime, so y prime, the product of those two elements, is in the image of f. So the image of f is closed under multiplication, it contains the identity, and finally, if y equals f of x is in the image, then y inverse, which is f of x inverse, is f of x inverse. So it's also the image of something. So the kernel and the image are subgroups. But there's one more thing I want to say about the image, about the kernel of a homomorphism. It's not just a normal subgroup. It says, so we have f from G to G prime, a homomorphism. K, which I'm going to call the kernel of f, is a normal subgroup of f. And so we have a group G mod K, and there's a homomorphism pi from G mod K. So the function pi from G to G mod K, defined by pi of x, is the left coset xk, is also a homomorphism. So what is the proof? Well, we know K is a subgroup of G. So an equivalent condition to normality, definition of normality, K is normal if for all elements x and k, we have gx, G inverses in K for every element in the group. I'll explain in a second why that's true, but let me just prove this. So that x be in K, G be in the group, so then f of x is the identity. That's what it means to be in the kernel. And what about f of gx, G inverse? So this is f of g, f of x, f of g inverse. That's f of g. F of x is the identity times f of g inverse, but that's f of g inverse, and an element times its inverse is the identity, which means gx, G inverse is in K. So I'll explain again, as I said in a second, why that means. Actually, I'll just do it right now. So this is just a lemma. There's a more detailed version of this in the notes. So K is a normal subgroup of G if and only if gx, G inverse is in K for all x in K and G in G. So proof. So let's prove it, say, in this direction first. So suppose K is normal. Then GK equals KG. So let G be in the group. The left coset equals the right coset. So therefore, if X is in K, then GX is in the left coset, which is the right coset, which means GX equals X prime G for some X prime in K, which means X prime is GX G inverse is in K. So if K is normal, if you take any element in K and any elements in the group, GX G inverse is in K. So that's the proof going from left to right. What's the proof going from right to left? So suppose GX G inverse is in K for all X in K and G in the group. So suppose we take an element let X be in G, sorry. Let X be in K. So there exists a Y in K, or I guess I call it X prime. There exists an X prime in K such that GX G inverse equals X prime, which means GX, I multiply on the right by G, is X prime G. This is an element of the right coset KG. So for every G in the group and X in the subgroup, GX is in the right coset, which means in particular, the whole left coset is contained in the right coset. And you can reverse the argument. For example, you can say, well, then, well, let's just say. So therefore, so this is true for all G. So G inverse K is contained in K G inverse. And if I multiply on both sides by G, I get G inverse KG is contained in GK G inverse G. This is KG, because this cancels, and this is GK. So I also have KG is contained in GK, so therefore GK equals KG, and K is normal. So K is a normal subgroup of G if when you take any elements in X and do what is called conjugation, conjugate by G, right? GX G inverse, that stays in K. Okay, so we've proved that we have a normal subgroup. So we have a quotient group. So G mod K is a group. So we have G and G mod K, and define a function pi from G to G mod K by pi of X is the left coset XK. So let's see. So must prove pi is a homomorphism. So let's see, pi of X times pi of Y is XK times YK is XYK is pi of XY. So the functional equation for a homomorphism is satisfied. Actually, so we're done. End of proof. And this is a very standard operation. So pi is called the canonical homomorphism. And we will study that in more detail in the next lecture.